Section 1. The New Frontier. Myth versus reality. We often look up at the night sky and see stars. We see the moon, perhaps a planet, shining with a steady light. But what if I told you that soon, we might be looking up at the internet itself? Imagine vast floating server farms orbiting our planet. These are the digital hearts of our modern world. The idea sounds like it was pulled directly from a science fiction novel, a grand vision of a future where our data lives among the cosmos. Is this just a futuristic dream, a flight of fancy for tech billionaires and space enthusiasts? Or is it a tangible reality that is already taking shape, piece by piece, high above our heads? It's a question worth asking, and the answer is more complex and fascinating than you might think. The myth is that massive city-sized data centers are being launched into orbit tomorrow. We picture structures reminiscent of the Death Star, but filled with servers instead of stormtroopers. This is the stuff of Hollywood blockbusters. It's dramatic and visually stunning, but it isn't the reality, at least not yet. The reality is something far more subtle, yet arguably more revolutionary in its implications. It's not about building giant structures overnight. It's about laying a foundation, one satellite at a time. It's about extending the digital infrastructure that already powers our lives from the ground into the final frontier. The first steps of this incredible journey are already underway, hidden in plain sight. The company at the forefront of this quiet revolution is one you already know well: Amazon. The same company that delivers packages to your door is now delivering data from space. Through its cloud computing division, Amazon Web Services, it's pioneering what could become the next evolution of the internet. This isn't just an experiment or a theoretical concept. It's a multi-billion-dollar investment in our planet's future connectivity. It's a plan to weave a digital web around the globe, ensuring that no corner is left in the dark. The question is no longer if we will move parts of our digital world to space, but how and when. This cosmic ambition matters to every single one of us, right here on Earth. This isn't just about faster streaming for your favorite shows or a better connection for online gaming, though that might be a side effect. This is about fundamentally changing how our world is connected. It could bring reliable internet to the most remote villages, revolutionizing education and economic opportunities. It could provide instant communication networks for disaster relief when ground infrastructure is destroyed. It could enable scientific breakthroughs by processing vast amounts of Earth observation data in real time. This is about building a more resilient, more connected, and more informed planet. The future is being built above us. Section 2. The building blocks of a space cloud. So, how is Amazon building this future? It starts with two key initiatives that are already in motion. Project Kuiper, massive constellation of satellites. Over 3,200 satellites. In low Earth orbit. Mission: provide fast, affordable broadband worldwide. Fast, affordable, broadband worldwide. Similar to SpaceX Starlink, monumental undertaking, billions in cutting-edge rocketry, billions of dollars. Advanced rocketry. Project Kuiper is the highway system for space internet. AWS, Space Cloud Services. The cloud meets the cosmos. AWS, world's largest cloud provider, extending the cloud beyond Earth's atmosphere. Services that let satellites process, analyze, and transmit data in orbit. Process, analyze, transmit. Satellites don't need to send all raw data to Earth. They can process data in space. Game changer for weather forecasting. Monitoring climate change. This is already happening. AWS partnership with NASA. JWST images and data hosted on AWS. AWS tested edge computing on the ISS. AWS snow cones sent to the ISS. Astronauts ran machine learning models and processed data in orbit. Proof: cloud computing can work in space. These tests are first steps toward a larger orbital network. Kuiper and AWS Space Services are two halves of one vision. Kuiper builds the global communications backbone. AWS supplies the intelligence and processing power. Together they enable data to live and be processed in space. Foundation for a true space cloud. It's slow, methodical, incredibly complex, but it's happening now, reshaping how we relate to data and the universe. Section 1. Project Kuiper, weaving a web around the world. Let's look closer at the first pillar of this grand design, Project Kuiper. This is Amazon's ambitious $10 billion answer to a fundamental global problem: a lack of universal internet access. The project's goal is to launch a constellation of more than 3,200 satellites into low Earth orbit. These satellites will work together, forming a mesh network that blankets the entire planet. Their purpose is to beam high-speed, low-latency internet directly to user terminals on the ground. This means reaching places where fiber optic cables have never been laid and where cell towers are a distant dream. It's about connecting the unconnected, from remote rural communities to ships sailing across the ocean. The scale of Project Kuiper is truly immense, a testament to the logistical and technological challenges involved. Building, launching, and operating thousands of satellites is a task of staggering complexity. Amazon has had to design its own antennas, its own satellite buses, and secure a massive fleet of rockets from multiple providers to get its hardware into orbit. The first two prototype satellites, KuiperSat-1 and KuiperSat-2, were successfully launched in late 2023. These initial tests were crucial to validate the technology in the harsh reality of space, ensuring that the satellites, the ground network, and the user terminals could all communicate effectively as designed. When people hear about satellite internet constellations, they often think of SpaceX's Starlink. Both projects share the same fundamental goal: using a large number of low Earth orbit satellites to provide global internet coverage. However, Project Kuiper is being designed to seamlessly integrate with Amazon's existing colossal infrastructure, particularly AWS. This isn't just about providing an internet connection. It's about creating a direct, high-speed on-ramp to the world's largest cloud platform from anywhere on the planet. This tight integration is a key differentiator and points toward a future far beyond simple web browsing for remote users. The timeline for Project Kuiper is aggressive. Following the successful prototype mission, Amazon is now entering its mass production and launch phase. The plan is to begin deploying operational satellites throughout 2024 and to start early customer pilots by the end of the year. The full constellation is expected to be deployed over the next several years, with the service becoming more widely available as more satellites join the network. This isn't a vision for the distant future. It's a project unfolding right now, with the first waves of a new global internet infrastructure scheduled to come online very soon. It is the foundational layer, the digital fabric being woven around our world. Section 2. AWS in the Cosmos. More than just storage. The second pillar of Amazon's space strategy is Amazon Web Services, or AWS, extending its domain into orbit. AWS is already the dominant force in cloud computing on Earth, providing the digital backbone for countless businesses, governments, and institutions. Now it's pioneering a new category of services specifically designed for the space industry, often referred to as AWS Space Cloud Services. This initiative isn't about launching massive data centers into orbit just yet. Instead, it's about creating the tools and infrastructure to help satellite operators and space agencies manage their data more efficiently on the ground and in space itself. A key service in this portfolio is AWS Ground Station. In the past, satellite operators had to build or lease their own expensive, geographically limited ground antennas. AWS Ground Station changes this model completely. It offers a global network of antennas that customers can access on a pay-as-you-go basis. This allows a satellite operator to download data and send commands from multiple points around the globe without the massive upfront investment. It democratizes access to space, allowing smaller companies, universities, and startups to operate satellite missions far more affordably and effectively than ever before. The collaboration between AWS and NASA serves as a powerful real-world example. The incredible data collected by missions like the James Webb Space Telescope needs to be stored, processed, and distributed to scientists all over the world. AWS provides the robust, scalable cloud infrastructure that makes this possible. The entire public archive of data from the telescope resides on the AWS cloud. This ensures that astronomers and astrophysicists have reliable and fast access to the petabytes of information that are unlocking the secrets of our universe, demonstrating AWS's capability to handle data of cosmic significance and scale. But the vision extends beyond just managing data on the ground. AWS has been actively testing the concept of edge computing in orbit. The experiment with an AWS snow cone device on the International Space Station was a landmark achievement in this area. It proved that data processing and even machine learning analysis could be performed directly in space. This reduces the need to send enormous volumes of raw data back to Earth, a process that consumes valuable bandwidth and time. Diagram a satellite in orbit. One data stream goes to an AWS ground station antenna, and another stream processes data on board using an AWS icon before sending a smaller, refined data packet down. Instead, a satellite can analyze images or sensor readings on its own, identify what's important, and send back only the valuable insights, making space-based systems faster and more autonomous. It is the combination of Project Kuiper and AWS Space Services that reveals the true scope of Amazon's ambition. These are not two separate projects running in parallel. They are designed to be deeply interconnected, creating a powerful closed-loop ecosystem. Project Kuiper will provide the ubiquitous high-bandwidth data transport layer. AWS will provide the computational intelligence and data management services that run on top of that layer. Together, they form the foundation for a new kind of global network, where the cloud is not just something you access from Earth, but a platform that extends directly into orbit and beyond. Imagine a satellite designed for environmental monitoring, tracking wildfires, or illegal deforestation in the Amazon rainforest. In the old model, this satellite would capture thousands of high-resolution images and spend hours or even days downloading that raw data to a ground station. A scientist would then need to process those images to find the one small area where a new fire has started. In the future envisioned by Amazon, this process could be revolutionized. The satellite could use onboard AWS edge computing to analyze the images in real time as they are captured, using an AI model to spot the telltale signs of smoke or cleared land. Once the AI identifies a point of interest, the satellite doesn't need to send back terabytes of imagery. Instead, it can transmit a small, focused alert packet containing just the critical information, the precise coordinates of the fire, its estimated size, and a cropped image. This alert could be beamed down almost instantly via the Project Kuiper network to the mobile device of a firefighter or a park ranger on the ground. This drastically reduces the time between data collection and actionable insight, from days to mere seconds. This synergy turns a simple imaging satellite into a real-time intelligent monitoring system, a powerful tool for disaster response and planetary stewardship. This foundational work is what paves the way for the more futuristic concepts of actual data centers in space. Proving cloud computing hardware can survive and operate in orbit, building the high-speed laser communication links between satellites, Amazon is methodically solving the core technical challenges. Each Kuiper satellite is not just an internet relay, it's a potential node in a future orbital cloud network. Each successful AWS test on the ISS is a proof of concept for more complex computational tasks in space. These are the crucial, deliberate steps being taken to transform science fiction into engineering reality. So, we've established that the building blocks are being put in place. But this begs a fundamental question. Why go through all this trouble? Why spend billions of dollars to launch complex electronics into the hostile environment of space? The first and most obvious reason is global coverage. On Earth, our internet is defined by physical infrastructure. We lay fiber optic cables across continents and under oceans. We build cell towers in our cities and towns. But this network has limits. It is incredibly expensive and difficult to extend this infrastructure to remote mountain villages, isolated desert communities, or ships in the middle of the Pacific. A space-based network simply bypasses these terrestrial limitations, offering a blanket of connectivity that can cover every square inch of our planet's surface. The second major advantage is a concept called latency, which is just a fancy word for delay. When you send data across the internet, it has to travel through a long, complex chain of cables, routers, and switches. If you're sending information from New York to Sydney, that data has to travel thousands of miles through undersea fiber optic cables. Light travels slightly slower in glass fiber than it does in a vacuum. A satellite network like Project Kuiper can create a shortcut. Data can be beamed up to a satellite, then relayed from satellite to satellite using lasers, traveling through the near vacuum of space at nearly the speed of light. This orbital express lane could significantly reduce delays, making global communication feel more instantaneous than ever before. Then there is the surprising benefit of cooling. Data centers on Earth are power-hungry beasts, and a huge portion of that power is used not for computing, but for cooling. Servers generate an immense amount of heat, and they need to be kept in constantly chilled, air-conditioned environments to prevent them from overheating. It's a massive and costly operational challenge. Space, on the other hand, offers a natural solution. The ambient environment is incredibly cold, dipping to hundreds of degrees below zero. By positioning a data center to radiate its heat into the void, we could potentially cool servers far more efficiently and with much less energy than is possible on the ground. It's like having access to the universe's largest refrigerator. These three advantages, universal coverage, lower latency, and natural cooling, form a powerful trifecta of incentives. They represent a fundamental shift in how we think about the physical constraints of our digital world. Universal coverage could bridge the digital divide, bringing educational and economic opportunities to the most isolated parts of our world. Lower latency could enable new technologies, from seamless global financial trading to truly immersive augmented reality experiences. And the promise of efficient cooling could help solve one of the biggest energy consumption problems of the modern tech industry. These are not minor improvements. They are transformative changes that could redefine the very architecture of the internet. Beyond performance, moving data centers to space presents a compelling environmental argument. On Earth, data centers have a significant physical footprint. They occupy vast tracts of land, often prime real estate for housing or agriculture. They also consume enormous quantities of fresh water for their cooling systems, putting a strain on local resources, especially in arid regions where many are built. An orbital data center, by contrast, would have zero direct impact on land or water use on our planet. It would float freely in its designated orbit, occupying a space that is otherwise empty. This offshoring of infrastructure into orbit could help preserve our planet's precious resources for other needs. Furthermore, space offers an unparalleled source of clean, renewable energy: the sun. A satellite orbiting Earth is exposed to constant, unfiltered sunlight. By equipping space-based data centers with large, efficient solar panels, they could be powered 24/7 with a completely green energy source. This stands in stark contrast to ground-based data centers, which are among the world's largest consumers of electricity, much of which still comes from fossil fuels. Harnessing solar power in space is far more efficient than on the ground, as there are no clouds, no atmosphere, and no nighttime to interrupt the energy supply. This could create a truly sustainable and carbon-neutral cloud infrastructure. Security is another powerful driver. Physical data centers on Earth are vulnerable. They can be targeted by physical attacks, earthquakes, hurricanes, or become pawns in geopolitical conflicts. A nation could sever an undersea cable or restrict access to a data center within its borders, disrupting global information flow. A network of data centers distributed in orbit would be far more resilient. It would be incredibly difficult for any single actor or event to disable the entire network. This creates a more robust and secure backbone for global communication, one that is less susceptible to the political and geological instabilities of our world. This concept of geopolitical neutrality is profound. An internet that lives in the internationally recognized territory of space could transcend national borders. It raises fascinating questions about data sovereignty and freedom of information. Who governs the data that is stored and processed in orbit? A space-based cloud could, in theory, provide a haven for data, protected from censorship or seizure by any single government. While this introduces complex legal and ethical challenges that we must address, the potential for a more open and resilient global information commons is a powerful motivation for building this infrastructure beyond the reach of terrestrial disputes and control. Powering the future of science and AI. The benefits of putting data centers in space extend far beyond providing internet to remote villages or making our video calls smoother. This new infrastructure could become a critical engine for scientific discovery and the advancement of artificial intelligence. Our planet is constantly being monitored by a growing fleet of Earth observation satellites. They collect staggering amounts of data on our weather, our oceans, our forests, and our changing climate. Currently, the bottleneck is getting that data down to Earth and processing it in time for it to be useful. An orbital cloud could change everything for these scientific endeavors. Imagine a constellation of satellites that can not only observe a developing hurricane, but also process that data in real time using powerful AI models running on nearby server satellites. These models could analyze cloud formations, sea surface temperatures, and wind speeds to generate far more accurate and timely predictions about the storm's path and intensity. The results could be beamed directly to emergency services and coastal communities, providing critical extra hours for evacuation and preparation. This turns our satellites from passive cameras into an active, intelligent planetary defense system, capable of helping us mitigate the worst effects of natural disasters. This same principle applies to deep space exploration. When we send probes to Mars, Jupiter, or beyond, they are limited by their onboard computing power and the slow, narrow data link back to Earth. A future with data centers on the Moon or in orbit around Mars could revolutionize our exploration of the solar system. Robotic rovers could offload their heavy computational tasks, like analyzing rock compositions or navigating treacherous terrain, to a local orbital cloud. This would allow us to deploy more sophisticated, autonomous robots that can explore faster and make more discoveries without constant guidance from human controllers millions of miles away. It's like giving our space probes a supercomputer brain in their own backyard. Ultimately, a space-based cloud could become the primary platform for training and running the next generation of large-scale AI models. These models require immense computational power, and building the necessary infrastructure in space, powered by the sun and cooled by the void, could be a more sustainable long-term solution. These orbital AIs could be tasked with solving some of humanity's biggest challenges. They could analyze global logistics for maximum efficiency. They could monitor the entire planet for signs of climate change. They could manage the complex traffic of thousands of satellites. They could sift through astronomical data in search of extraterrestrial signals. Putting our data in space is not just about storage. It's about building a brain for our planet. The hardware of the heavens. So, How do you actually build a computer that can survive in space? It's not as simple as launching a standard server rack into orbit. The first major hurdle is radiation. Earth's magnetic field and atmosphere protect us from a constant barrage of cosmic rays and high-energy particles from the sun. In space, this protection is gone. This radiation can wreak havoc on delicate electronics. Data corruption, short circuits, complete system failure. To counter this, Amazon would need radiation-hardened servers, special materials for shielding, redesign microchips to be more resilient, build redundancy so a zapped part is taken over by another. It's about building a digital fortress on a microscopic level. You can't send a technician to fix a broken server. There are no IT support crews in space, so the data center must be a masterpiece of automation and robotics. Systems must self-diagnose. Systems must self-heal. If a memory module fails, detect the fault. Isolate the damaged component. Reroute processes to a backup module. No humans required. For physical repairs, replacing a failed power supply, or replacing an entire server blade, you'd need a small fleet of maintenance robots inside the structure. Robots ready to perform intricate mechanical repairs autonomously. The physical form of these servers would be completely different from terrestrial designs. On Earth, servers sit in racks with gravity holding them and fans for cooling. In zero-G vacuum, that approach is useless. Instead, modular servers. Each one sealed and self-contained. Maybe a cube, maybe a slab. Modules conduct heat to their outer casing. The casing acts as a radiator, shedding heat into the cold void. This makes them easy for robots to handle and swap, like futuristic Lego bricks. Finally, power. The sun gives abundant energy. You need a reliable system to capture and manage it. Large, efficient solar panels. Panels that track the sun as the data center orbits. Robust battery systems to store power for when the satellite passes through Earth's shadow. Power architecture must be highly resilient with multiple redundancies. A power failure in space isn't an inconvenience. It can turn costly infrastructure into silent, frozen space junk. Every component must be built for ultimate reliability. The software and the signals. Building the hardware is only half the battle. Connecting these orbital servers into a cohesive network presents another set of monumental challenges. The key technology that makes this possible is laser-based satellite communication, also known as optical inter-satellite links. Instead of using radio waves, satellites can communicate with each other by firing highly focused beams of light. These lasers can carry enormous amounts of data, far more than traditional radio frequencies. They allow information to travel at the speed of light through the near vacuum of space. This is the technology that allows an orbital network to bypass the slower fiber optic cables on the ground, creating a true data superhighway in the sky. This network of lasers needs to be incredibly precise. The satellites are moving at over 17,000 miles per hour, and they need to maintain a perfect laser lock with each other over distances of hundreds or even thousands of miles. This requires sophisticated pointing, acquisition, and tracking systems that can constantly adjust for the satellite's movements and vibrations. The software managing this network must be exceptionally intelligent, capable of dynamically routing data across the constellation. If one satellite's path is temporarily blocked by the Earth or another satellite, the network must instantly calculate a new path for the data to travel, ensuring there are no interruptions in service. It's like a cosmic game of connect the dots played at lightning speed. The software running on the servers themselves would also need to be specially designed for this unique environment. It would have to be hyper-aware of the hardware's status, constantly monitoring for radiation-induced errors, or bit flips. Error-correcting codes and fault-tolerant software architectures would be essential to ensure data integrity. The operating system would need to manage the unique thermal properties of the system, perhaps throttling down processors if a part of the server is facing the sun and heating up, then ramping them back up when it returns to shadow. It's a constant, delicate dance between performance and survival, all orchestrated by layers of sophisticated code. Amazon is not starting from scratch here. The AWS snow cone experiment on the International Space Station was a crucial proof of concept for this kind of software. It demonstrated that a small, ruggedized server running AWS software could function effectively in a microgravity and high radiation environment. The astronauts were able to run machine learning models directly on the device, processing data captured in orbit. This test provided invaluable data on how to design software that can handle the rigors of space. It was an early, but vital, step in proving that the cloud software can be adapted to work far beyond the safe confines of a terrestrial data center. Section 3. Putting all these pieces together, what would a fully realized space cloud architecture look like? It likely wouldn't be one single monolithic data center. Instead, it would be distributed and modular. One concept is the server satellite, a large constellation like Project Kuiper. Communication gear, processing capacity, storage capacity. Thousands of these satellites would work together, a massively parallel distributed computer encircling the globe. This offers incredible resiliency. Losing a few satellites barely affects the network. A second tier would be dedicated server stations, larger, purpose-built floating data centers, not for human habitation. Dense racks of modular servers. Robotically maintained systems. Stations in strategic orbits act as major processing hubs. For example, a geostationary server station providing continuous high-power compute to a continent, acting as the central brain for thousands of lower orbit satellites. These are the heavy-lifting powerhouses. Layers in orbit plus the ground create a tiered computing system. At the edge, a user on Earth with their Kuiper terminal. Data uplinks to the nearest server satellite. Simple, low-latency tasks processed on that satellite. Complex tasks relayed via laser links to other satellites, or uplinked to large server stations for heavy processing. Final results beamed back down to the user. Hybrid architecture, edge computing benefits, plus centralized cloud power, all orchestrated in orbit. This extends what AWS does on Earth. AWS runs global regions and local zones. The Orbital cloud adds a higher layer, large server stations, analogous to AWS regions. Thousands of server satellites, like space local zones. Adapt a proven model for the final frontier using lasers, robots, and radiation-hardened hardware to build the next generation of global infrastructure. Section 1. While the vision of an orbital cloud is breathtaking, the path to building it is paved with immense and costly challenges. The single greatest barrier is the astronomical cost of launching anything into space. Every single server, every solar panel, every robotic arm must escape Earth's gravity, and that requires an incredible amount of energy and money. Even with the advent of reusable rockets, sending the sheer mass of hardware required for a data center into orbit remains prohibitively expensive. We are not just talking about a few satellites. We're talking about thousands of tons of delicate, heavy equipment. This economic reality is the primary brake on realizing this futuristic vision quickly. This weight problem is compounded by the fact that server equipment is dense and heavy. A single server rack on Earth can weigh over 1,000 pounds, and a full data center contains thousands of these racks. To put even a small-scale data center into orbit would require a long and expensive campaign of heavy-lift rocket launches. Amazon's own Project Kuiper, which involves launching over 3,200 relatively small satellites, is a $10 billion endeavor. A project to launch actual server farms would likely cost many multiples of that, a financial gamble of unprecedented scale. The cost per pound to orbit must fall dramatically before floating data centers become economically viable on a large scale. Beyond the initial launch, there's the ongoing cost and complexity of maintenance. On Earth, if a server fails, a technician can walk over and replace it in minutes. In space, a failed component requires a complex pre-programmed robotic mission to fix it, if a fix is even possible. Developing these highly sophisticated autonomous maintenance robots is a massive technological challenge in its own right. The systems must be near perfect, as a software bug in a repair robot could lead to mission failure, rendering a billion-dollar asset useless. The requirement for near-total autonomy adds layers of complexity and cost to every single piece of hardware designed for the system. Finally, we must consider the risk of a launch failure. Despite modern advancements, rocketry is still a risky business. A single catastrophic failure during launch could destroy hundreds of millions of dollars worth of custom-built, radiation-hardened server equipment in a matter of seconds. To build out a full orbital data network would require dozens, if not hundreds, of successful launches. The financial and programmatic risk associated with each one is enormous. This high-stakes reality forces engineers to build extreme redundancy into every system, which further increases weight and cost, creating a difficult cycle of escalating expenses that tempers the grand vision with a dose of harsh economic and physical reality. Section 2. Once the hardware is in orbit, it faces a new set of relentless threats from the space environment itself. Chief among these is space weather. Our Sun is an active star. It regularly unleashes solar flares. It also produces coronal mass ejections. These events send massive waves of charged particles hurtling through the solar system. A powerful solar storm could easily overwhelm a satellite's shielding. It can fry sensitive electronics and render a satellite completely inoperable. Some shielding is possible. Some hardening is possible. But a particularly strong direct hit could be catastrophic for an orbital data center. It could wipe out a critical piece of infrastructure with little to no warning. This constant, unpredictable threat requires resilience far beyond what's needed on Earth. Another, more man-made danger is the growing problem of space junk. Decades of space activity have left a cloud of debris orbiting our planet, from defunct satellites, from spent rocket stages, to tiny flecks of paint. There are hundreds of thousands of objects large enough to be tracked, and likely millions more that are too small to see. Even a tiny object at over 17,000 miles per hour can strike with the force of a bomb and destroy a satellite. As constellations like Starlink and Kuiper add thousands more satellites, the collision risk increases. Collisions create more debris, a cascading effect. This scenario is known as the Kessler syndrome. Then there is the profound legal and ethical vacuum of space. Existing treaties like the Outer Space Treaty of 1967 were written long before commercial orbital data centers. This raises a host of thorny questions. Who has legal jurisdiction over data in a server satellite? If a U.S. company's satellite stores a European citizen's data, which laws apply? What prevents a nation from using this infrastructure for espionage? What prevents using it for unfair geopolitical advantage? These vague, untested laws create a Wild West environment. That could lead to international disputes over data, over privacy, over sovereignty. Finally, moving critical infrastructure into space creates a new vector for conflict: a space-based internet, a space data cloud. In conflict, orbital data centers could become primary targets. An anti-satellite weapon could knock out access to a country's cloud, crippling economy and communications in an instant. This weaponization of space is a serious risk tied to commercialization of orbit. Building our future in space means being prepared to defend it, adding yet another layer of complexity and danger. Section 1. We stand at a fascinating intersection of ambition and reality. The notion of Amazon building vast data centers in space is not the immediate science fiction spectacle. It's not about launching city-sized server farms. The reality is more methodical, more strategic. It is a future being built piece by piece through foundational projects like Project Kuiper Satellite Constellation, AWS Space Services, We have seen the powerful why driving this push into orbit. The promise of total global coverage, the speed of laser-based communication, the elegance of natural cooling, and the potential for a more secure, sustainable, geopolitically neutral internet. This is not just a technological curiosity. It is a potential solution to some of our planet's most pressing challenges. However, this grand vision is anchored by the immense gravity of its challenges. The staggering cost of launching mass into orbit remains the single greatest barrier, turning every pound of hardware into a precious commodity. Once in orbit, this infrastructure must survive the relentless bombardment of solar radiation, the ever-growing threat of space junk. It must operate with near-perfect robotic autonomy, as there is no IT help desk in the void. And it must navigate a murky, undefined legal landscape where questions of data ownership and jurisdiction float as freely as the satellites themselves. These are not trivial problems. They are monumental hurdles that require breakthroughs in engineering, economics, international law. So, what does the near future hold? The next 5 to 20 years will be a period of rapid, incremental progress. By 2026 or 2027, we can expect Amazon's Project Kuiper to begin its commercial rollout, providing a new layer of global internet connectivity. Soon after, we will likely see the first dedicated orbital cloud servers deployed, serving specialized clients like military agencies, research institutions, AI companies that require high-speed, in-orbit processing. This will enable real-time Earth monitoring and power-complex deep space missions. Further down the line, as we push our presence outward, we can realistically envision small data nodes on the Moon, Mars, supporting NASA's Artemis program and the first steps of human colonization. This journey out into the cosmos brings us back to a profound question for us here on Earth. As our digital world migrates from the ground to the heavens, we are forced to reconsider our most fundamental concepts of information and control. This evolution from a terrestrial internet to an orbital one is more than just a technological upgrade. It is a philosophical shift. We must ask ourselves, if the internet truly moves to space, a domain owned by no single nation, will the old rules of borders, censorship, control over information still apply? The answer to that question will shape the future of human knowledge and freedom in the 21st century and beyond.